Hello, welcome back to lectures. Today we're going to pick up pretty much where the last lecture set on probabilities left off. This one's about distributions. So if you might remember from the last lecture, we were dealing with probabilities and ended with the idea of a normal distribution where, remember, each of these histograms is really representing this smooth curve here as a summary version of a lot of bar graphs. So a histogram and this normal distribution here are actually the same thing. So the probability distributions that we dealt with last lecture lead up to a normal distribution. Note that it's not a paranormal distribution. And so what we're going to do here today is talk about how do you evaluate a data set to find out if it actually is normal. And then we need to also address some other kinds of distributions. The normal distribution is classically assumed for traditional analyses that we're working with this semester. For example, analysis of variance, regressions will assume normal distributions. But we need to be careful about that, and there are times when we need to actually represent our data as another distribution, the ones that you see listed here, which we're going to walk through briefly. And in fact, modern, I would say more advanced statistical methods now enable us to be able to deal with those kinds of distributions better than some of the classic methods where you're locked into an assumption of a normal distribution. Okay, so what do we mean when we say normal distribution? Well, you might remember this figure from the previous lecture. That is what I was talking about with a histogram, where those actual data for heights among people look close to the hypothetical expected normal distribution. And you might say, if you're just eyeballing that, that's not bad. Well, a normal distribution is called normal because it's assumed to be that general shape if you have lots and lots of data points. In other words, it's the most common distribution given essentially an infinite number of data. And so if you kept collecting data on heights of people, eventually that wobbly looking shape that's almost normal would look closer to the one that we have up here. Okay? So the idea is that this typical normal kind of distribution would eventually sort out with lots of data. And notice that it's very nicely symmetrical left and right. This is a unimodal distribution in that it has one peak, one mode in the middle. And it's symmetrical around the mean, left and right of that center point. Remember, one more time, that this is simply a count, a histogram of how many individuals were in a certain bin or a certain category here. And the finer the number of bins, the finer the width of those bins, the more fine scale your curve could become, right? This is again assuming you have lots and lots of data to fill those bins. Okay, this is related to other curves that you'll see in just a little bit, but the difference between this and other curves, one more time, is that it's beautifully symmetrical left and right of that mean point. It is not necessarily going to be symmetrical for some of the other distributions. So the normal distribution can vary in the width and the height, if you will, of the curve. Notice that the two I'm showing here have different numbers on the x-axis, okay? So it's centered here around 0, and then it steps out 1, 2, 3 units, which we're going to talk about in a second, to the left and to the right. This one is representing non-centered data, and it might vary by quite a bit more, 12 units, let's say, of some kind of variable. So these distributions actually, if you were to graph them out on the same number scale, would look rather different. This one's centered on 0 and only varies by 1, 2, 3 units. This non-centered one, non-standardized one, has quite a wide shape and not, in fact, as high a peak as you might expect otherwise, okay? So a standard normal distribution has this center of 0. So basically what we've done is move that mean here into the middle, okay, and I'm sorry, into the middle, to be counted as 0 instead. So then we count how many negative from 0 and how many positive from 0, whereas of course this is not centered around 0, and these values are then negative on the left, not negative on the right side, okay? So a standard normal distribution is standardized, centered on 0, and what we're doing is expressing proportions of the total area under the curve in these bands. So 1 band, 2 bands, 3 bands, and those belts that we're going to look at in a moment are called standard deviations. I say look at, we're going to talk about the equation. And so one standard deviation is one standard way of talking about how much variation there is away from the mean, okay? And notice that if you take the sum of squares there, that standard deviation squared is actually variance, okay? That variance is going to be simply 1 because the square of 1 is 1. So the standard normal distribution is then an easy way to talk about variance and its square root, which is standard deviation. Okay? The curve can be stretched with different variances and different standard deviations and centered elsewhere, of course, but the standardized version is now based around 0. And so this normal distribution really is nicely described by the standard deviation. That is the key to thinking about how far away you are from the mean on any normal distribution that is centered on 0. One standard deviation is very conveniently just called z. So that's 1 unit of z. So we can talk about any normal distribution then as a z distribution. How many z's away are you from a mean is an easy way to think about comparing any given standard normal curve to any other curve. Okay. Now, every observation is some part of a z away from the mean then, right? You might be 1.5 z's away. You might only be 0.1 z's away from the mean. The z is simply this. Okay. Remember, this is a standard deviation. So it is the number you have, the individual observation, and how far away it is from the mean. So the individual minus the mean is showing the difference from the mean, right? Divided by our standard cutoffs, our standard z units. So I might be just a little bit away from the mean, and so if it's less than 1 standard deviation, I'm going to have a fractional z. If this is greater than 1 standard deviation, obviously I get a 1 point something z score, right? And observations with an absolute value of z that are greater than some sort of possible number here are then less possible. So if I wanted to think about a low probability, this here we go. Let's think about it this way. If you take your score on an ACT, you get a percentile score, right? So this would be a relatively low percentile score on an ACT or SAT, GRE exam, something like that. And so a low percentile score means that you scored higher than all the people to that end of the distribution. A higher curve score means that you scored better than the average bear. Okay? So a z-score is simply a way to talk about those percentiles. Now we can look at this more finely if you wish to. This just keep in mind that z's are just simply standard deviations. So every truly normal curve can be described by the mean, the standard deviation, and thus how many z's away you are. Okay? We know the probabilities are percent chance because remember every one of these things is a count of individuals in a distribution. We know that these, if they fit a nice normal curve with lots and lots of observations, which was always going to be the case with lots and lots of observations, we know that there's a percent chance of finding that individual if you sample again at random with that kind of a measurement. So again, if this is, for example, heights of people, there's going to be an average height if we measured all the people out there, and we're going to find this beautiful, nice, smooth distribution. And the probabilities of finding somebody who's very short are quite low. The probabilities of finding somebody very, very tall are also quite low. Most people are going to be somewhere in this middle pack. So 1 z or 1 standard deviation away from that centered mean, give or take, is 68% of the variation. 2 standard deviations away, 1, 2 out, either way, is 95%. This is convenient. It's actually really close to 95%. It's a fractional difference. So the point is we can round off and talk about this as a 95% of the data fitting within 2 standard deviations away. 2 standard deviations, 1, 2 away from the mean, either way. Okay, so we're talking basically about an error bar that encompasses here 95% of the values around a mean. Okay, if you want to go 3 standard deviations, 1, 2, 3, you've encompassed almost all the data, 99.7% of the variables. Okay, so we have an easy, standard, simple way to talk about any estimate you have and compare that then to another estimate. So let's say we wanted to compare, I don't know, heights of men of the world compared to heights of women of the world. We might have a mean plus or minus a standard deviation, or let's say 2, and be able to compare that to another bell curve that might be slightly displaced. That's the basis of a lot of comparisons we're going to be doing. So another way to think about this might be if you had a lot of random samples, a shotgun pattern in 2 dimensions, but if you map that from left to right across here, most of those pinpricks on the target would be around the middle and very few of them way out to the edge. Think about if you're throwing darts, and if you're actually any good at this and haven't had too many beers into the night, you might be mostly somewhere around the target, not too many off onto the wall. Okay, so we have lots and lots of random samples. Eventually it will settle down to a really nice, smooth, normal distribution. We're assuming that there's no extra processes involved. It's simply this random sample of a very large number of individuals. Individual darts, individual BBs, whatever we want to talk about, okay? So that data should then resemble a normal distribution. There's nothing else skewing it. It's going to be this cloud of points that are wrapped around this center point, okay? And if that's the case, then we can talk about data in a really convenient way, and it will be very easy to compare a bell curve like this to some other bell curve. Well, let's think about this a little bit more. If we remember that 2 standard deviations is about 95% of the data, and so values that are less than that are only 2.5% off to the left, and values greater than that are going to be values that are in the tail way off at the upper end, the upper 2.5%. So 1 minus that 2 standard deviations is 5%. And so this is where our convenient cutoff of a p-value of 0.05 comes from. It's just it's just a custom that we've all been using for a long time, where we're talking about the tails of the distributions, the oddballs out there at the extreme upper end or the extreme lower end of a normal distribution. Those represent only 5% of the data, and so we've become accustomed to talking about the chances of a number being different from what we expect in a normal distribution, and the pretty strong, I gotta say, pretty strong cutoff is a 0.05. We're really expecting something to be way out in the tails to say it's quite different from the rest of the points we have in a normal distribution. So if we think about how many multiples of sigma you want to go out there, you can go beyond the 2 that we're accustomed to in science. There's talk in design and engineering of 6 sigma, 10 to the minus 6 probabilities. So if you're engineering something, for the space shuttle, you want to make sure there's a very low probability of failure. So they really work hard at maintaining very low chances that something like that might occur. And they talk about it in these sigma units, okay? It's the same thing we talk about. What if you don't have a really large n, though? All of this is assuming that you have really large sample size. Or what if the data are not going to be so nicely symmetrical, which is more likely the case if you don't have a really large sample. You might get into some oddball skewed distributions. And how do you know if it's normal? If you're expecting this beautiful bell curve, what if you look at a data set and you're trying to judge that just by eye? It might be tricky. So there are some tools for that. So if you're evaluating normality and you want to make sure that you're not looking at some sort of little strange, rare kind of observation like that, then there are a couple different tools to play with. What most texts talk about would be visual tests. I myself am a little uncomfortable with that because you might see a normal curve there and I might see Nessie. So it's a little bit subjective to talk about visual tests. It's important to look at the distributions. I'm not saying you shouldn't. I'm just saying that it's also kind of reassuring to do an objective test, a statistical test. So this is a classic test that I'm showing you here, Shapiro Wilk test, and I'll explain why in just a moment. But it's also a beginning example that we're going to be dealing with the rest of the semester, where you might look at a scatter plot and you might be able to say, well, the line kind of fits that pretty well. But it's nice to have an objective measure of that, right? You like to be able to say, and it has this kind of a score on a 0 to 1 scale. That's essentially the idea here of a Shapiro-Wilk test. It supplements the visual feedback you get from looking at a histogram to decide whether or not something is normal. So we're going to look at a couple different ways to visually examine these, and then I'll also briefly introduce you to the Shapiro-Wilk test. So for evaluating normality visually, you can do it a couple different ways. Simply plot the histogram of what your data look like and see if it looks visually close to an expected normal distribution. And so you would say, well, that's not bad. It's pretty close. Most of the bars are fitting pretty near the line. That one's above, this one's below, but for the most part, it looks like it's sort of normal. And that's often how people would evaluate this if you're just looking at something visually. Another very nice way to do this, which we're going to be dealing with all semester, is a normality plot, where it basically takes that curvy line there and stretches it out into a straight line, and then you're looking to see if your points that would count towards the histogram fall along that line. This is breaking things into quintiles. We're looking at segments of this line, in other words. It's a cumulative probability distribution kind of approach. So if we have the heights distributed along that straight line, you would say the points fit closely to your expected line. That's very nice. Okay, so what is this plot? The observations are ranked and expressed as percentiles, and we're using that z-score thing again, okay? The quantiles of standard normal. So this essentially snaps that smooth curve onto that straight line and compares your points that you actually observed to that theoretical bell curve that you see here in another example with the the dashed red line. So if the points fall on the bell curve, you should see the points very nicely close to your straight line in this. It's a little more carefully plotted than this one, where you're trying to evaluate broad histograms compared to a curvy line at the same time. Now what we're doing is stretching that out onto a straight line and snapping the points to it. All of the points, by the way, that contribute to your histogram, so you can more visually you are more visually able to detect a pattern. Here's a couple of examples. Here's 3 different ones, and you can see that this one's fitting pretty well just visually, maybe better than this one where it has a few gaps and a few spikes above. This one's clearly more spiky and gappy than the bell curve. So we have a gradient across from left to right where we're looking at basically kind of a crummy fit, but not too bad, towards maybe towards looking pretty good. All right. So if we look at the curves down below, you can also see that you get a little bit more wiggle on the blue and on the left around the straight line. The green is fitted closer to the straight line, and the yellow on the right is quite close to the straight line. And that's essentially confirming what you might have inferred with the eyeball version of your histogram here. Okay. Here's another example. These are actual data for the heights of NBA players. And again, we have the theoretical expectation of what the bell curve should look like compared to the histograms. And you can see that there's a substantial number of points above the bell here and a fall below it here. So anytime you see a dip below, like here, you can see that the points fall below your expected straight line for the normality plot, and you get a slight blip above the line there too. So you might say there's a little bit of a zigzag, a seesaw, kind of going back and forth on the actual data. And you might visually say, well, it's not too bad, and here's why I feel like this can be a little bit wishy-washy. Let's take one that's quite a bit more different. If you take this one, here's the normal distribution expectation again. This is for poker earnings in US dollars. You can see a lot of people are centered pretty much around breaking even. And by the way, some could be losing up to 500 or gaining up to 500. So most of the odds are going to be not too well in your favor, right? For the most part, only earning a little bit, perhaps losing some. A few people have made quite a bit. Those outliers, if you will, way out here, are going to be the ones that are contributing to this point that comes way up above anything like a straight line. So it's going to be pretty hard to draw a straight line to this curve that curves way up here. And this is saying you have a much higher number of them than you might expect according to the normal distribution. There's a spike of those people out here who seem to be rather good at this. Not me. So this is pretty clearly not representing a normal distribution, and you might have guessed that from here as well, but this makes it a little bit easier to judge that compared to, for example, this one, which was not bad. Okay, well, so you might have the sense already that I'm a little uncomfortable with these visual tests, and so I've often wanted to go to something that's a bit more objective. All right, so let's talk about the Shapiro-Wilk test. It's a pretty simple test. It'll be very easy for you to produce this in R. In fact, lots of stats packages do this. The idea is that it computes a statistic, like a lot of statistical tests do, and it compares that statistic for your data to what you would get if you had a normal distribution. And it's all based on the sum of the squared deviations away from a mean. So remember, you had your number, and you compare that how far away it is from a mean. If you square those, what's that doing? It's just simply taking any of the negative values, the ones that fell down to the left below the mean, and making them positive. So if all the differences of all the deviations are squared, they all become positive numbers, and then we can add them up. And we get a measure of the spread around the mean, essentially, right? And you compare that to an expected version of a really nice, beautiful normal distribution. So there is a paper recently in 2011 which finally got around to saying, how well does the Shapiro-Wilk test work? And I quote straight out of their paper that says that it is the most powerful normality test, followed by some other ones you might have heard of. One that has been used fairly often is the Kolmogorov-Smirnov test, and notice that it falls down to the bottom of the list. But also note that they're saying that the power of all four tests is low if you don't have enough samples. So once again, we're going to be talking about collecting lots of samples if you can get away with it, if you can afford it, because you have a better chance of saying that my data fit the assumptions that I need for my statistical analyses. How many is enough? A good rule of thumb over and over again has been you need about 30 individuals for every treatment group, for every zone of things that you want to try to compare to another zone. So if we're talking about our helicopter experiment, it would be a treatment combination, wing length and body length and all that kind of stuff combined. We need at least 30 of those to be really confident that we can estimate if it's a normal distribution or not. If you're looking at a regression, you're talking about a bunch of points up and down the line. You want 30 at a bunch of different places up and down that line. Okay. So for evaluating normality with a Shapiro-Wilk test, you would simply say Shapiro.test of some data, and you would get this kind of a result right here. And so if we do that for the original data, we can find that it is not normal in this case. Okay. But if I take the log of that, the log would be a way to help make data fit a normal distribution better. You notice that it works nicely. So what this is saying is that there is not a significant difference from a normal distribution here once we've taken the log. So we'd like to see that kind of a number for a Shapiro test. We don't want to see this kind of a number for a Shapiro test where it says it is significantly different from a normal distribution. Okay, so that's a convenient objective measure of normality that makes me feel a little bit more comfortable with when I eyeball a normal distribution plot. I'm sort of calibrating what I expect to what I can see with an objective test like this. So I'm not saying don't do those visual tests. They're important. It helps you see your data, just like everything else we're going to be doing with graphs and data analyses. But I think this is a convenient double check of your subjective measure because you're using an objective test. All right. So Shapiro tests are going to be very easy to do, and they will be important before you move into statistical analyses, because a lot of these assume a normal distribution, and we're going to find that there are data sets that actually fit another kind of distribution better. So nicely, we can address those with some of the other more advanced statistical tests that we have. So what are some of these distributions? What do they look like? Well, there's four basic types we're going to talk about here. There's others, but these are the main ones, I think. A geometric distribution is one that has an exponential decay or geometric decay. It's essentially like a half-life curve. It doubles or so after a certain number of counts out. So it's used to classically estimate the waiting time until you see a success. So think about this as the probability that if you roll dice, eventually you would get a certain number that comes up. Okay, so maybe that's a way to get there. Waiting time until a success. So this is for independent and identically distributed random variables where the outcomes are binary. Okay, binary. I'm sorry, I should have said instead of rolling dice, we're tossing a coin. So how many trials would it take to get a certain number of outcomes? Okay, a geometric distribution is easy to talk about if you're tossing a dice, for example, before you get a 2. So if 2 counts as success and anything else is a failure, then the sample proportion p is simply the number of successes out of the total number of trials, right? And this is all thanks to Bernoulli, who figured these things out. And that's quite the wig, eh? So anyway, we tossed a dice 20 times, and I rolled a 2 4 of those 20 times. The success to failure rate is simply a Bernoulli variable, 4 out of 20. Okay, so something that simple could get you a portrait painted those days. I think it takes a little bit more than that now. If you have a chance of not rolling a 2, well, let's see. It would be the 1 minus p, right? If p is 4, we had I rolled a 2 4 times, yes. So 1 minus p, it would be the chance of not rolling a 2, all right? And the mu, the number of times to roll a 2, is just simply p. How many times to be able to roll a 2, okay? So the standard deviation of this is the square root of these two things, okay? That's a Bernoulli distribution. There are other kinds of distributions we're going to bump into as well. I should say it was a geometric distribution represented by Bernoulli. There's another distribution you're going to find quite often, I think, that's going to be helpful to you. It's called a binomial distribution. It's the probability of having exactly a certain number of successes. How's that different from what we had before? The geometric distribution was the probability of how many times before you get a success, okay? The probability of getting success. Notice what the binomial is? The probability of getting exactly a certain number of successes. So you're trying to predict if you roll that dice 20 times, how many 2s would you get, okay? Now, one of the interesting things about a binomial distribution is the more samples you get, eventually it approaches a normal distribution. So if you had only 10, it can be rather skewed. But by the time you get up to 30, it's starting to look more normal-like. By the time you get up to 100 samples, it's pretty good. By the time you get up to 300 samples, it's even better yet. So notice that this can be convenient then if you're dealing with a fewer number of samples, because you might not be able to obtain a normal distribution with relatively few samples. It's getting close by the time you get to 30, that rule of thumb we have. But fewer than 30, you might be thinking about binomial distributions quite a bit. And this probability of having exactly a certain number of successes then can be used for a number of different kinds of data. So let's think about this just briefly. For the probability of having exactly k successes in n trials, what is that? The probability of success, p, is the n minus k. We can think about it this way, the number of failures. So the probability of a single scenario is p to the k times that number of failures, times 1 minus p, and then raised to the n minus k, the number of failures. Okay, for a single scenario we get this equation. For more than one scenario, we have to start thinking about it as a factorial, where it gets adding up all the different possible outcomes that you get. All right, so we're not going to really deal with this equation much. I just want you to think about it. It's simple in that it deals with counts of failures and successes, and then the multiple kinds of probabilities you can get with multiple kinds of successes. All right. So the binomial distributions, you can substitute all these terms, and you get a pretty sophisticated looking equation here that's calculated by factorials. What is all that saying? I'm going to go for it. I'm going to say this. It tells you the probability of observing exactly k successes in n independent trials, all right, that's what all this is saying, is equal to the number of ways to choose those k successes in that number of trials, n, times the probability of any one of those scenarios coming true. I hope that makes some sense. It's a binomial distribution if the trials are independent. Each roll of the dice has nothing to do with the roll before. The number of trials, n, is fixed. You know how many trials you're going to toss that dice. Each trial outcome can be classified as either a success or a failure. Did I get a 2 or not? Simple. Okay? And the probability of success, p, is the same for each trial. If I'm rolling a dice, the probability of getting that 2 is 1 out of 6 sides of the dice, right? Okay, so binomial distribution, then we have that equation. What's the probability of, let's say, rolling a 6 on 5 out of 5 tosses? In other words, what are the chances I'm going to get a 6 every time I toss a dice 5 times? Okay, so I know I'm going to toss it 5 times. I know what the success rate is I'm expecting, 5 out of 5, and the chances of getting that is actually only 1 out of 6, right? Because it's a 6-sided dice. So I calculate what the factorial of n is, and I calculate the factorial of k, and I plug and chug through my equation, and you can see that the odds are quite low. I would take about 100,000 tosses before I could observe that happening 13 times. I would get 13 events of rolling 5 times in a row where I get 6 every time in 100,000 tosses. The chances of it happening 1 are pretty low odds. So I don't think I'm going to be putting bets on that one at the casino. That's not something that's going to come up very often. All right, a binomial distribution gets hard if you have a whole lot of trials then, right? But fortunately, the normal distribution looks a lot like that binomial. Remember that shift happened when we got larger and larger sample sizes. So when you get up to np and n1 minus p greater than 10, it's not bad. It's a pretty good guess that it's going to be close to a normal distribution. It's a rougher guess if you're only dealing with a really narrow distribution. So if you have lots of numbers, you can say it's going to fit this pretty well. But if I'm only playing with a few numbers, it's more of these stair-step kind of things, and it's not going to fit very well to that normal distribution. You're better off playing with a binomial. Okay, so There is, interestingly, a whole different one called a negative binomial, and describes the probability of observing the certain number of success, the kth success, okay? The, the sixth success in that certain number of trials, let's say, all right? So it's more specific than the plain binomial. You're waiting for a certain event, a certain success to happen. What's the probability that will happen on a certain trial, a certain toss? So it's another pretty complicated formula where again we're assuming trials are independent. The trial outcome can be classified as simply as a success or failure, and the probability is the same for every trial like we had before. But what we're counting is the probability of seeing that last one that we're watching for being a success. Now, you don't think about collecting data and tosses of the dice, etc. very often, but these distributions turn out to be handy if you're talking about counts, if you're talking about observations of organisms, for example. So, how's this different from the plain old binomial? You're dealing with a fixed number of trials and consider the total number of successes in that plain binomial. In the negative binomial, you're considering how many trials are needed to get a fixed number of successes. Okay, so all of that is waiting to finally hit that snake eyes or whatever if you're rolling dice. Okay, so it's this complicated formula with a bunch of these variables. We're not going to sweat that too much. All I'm going to say is that binomial and negative binomial distributions can be really nice when you're dealing with, I'm going to go back to this graph again, we're dealing with a skewed distribution that can't be quite normal again. So if you have fairly few samples and it's really hard to say that your data are looking very normal, a binomial and indeed a negative binomial distribution can be very handy to work with, and as an alternative then to the standard normal distribution we assume with lots of classic data analysis methods. All right. Enough about binomial and negative binomial. Let's talk about Poisson distribution. The Poisson distribution is kind of related in that we're also seeing a skewish kind of distribution here. Okay, it can have a different shape to it than a binomial or negative binomial, and it's for estimating the number of rare events in a large population over time. So an example from a book is the number of occurrences of acute myocardial infarction on a whole year in New York City. Okay, so the number of occurrences on those 365 days would be a pretty decent number, and so very few of those days would be really lots and lots of those. Most of the days that we collected the data in had only 4 or so in a large population in New York City. So the Poisson distribution generated by this very, I don't know, contented looking fellow here, Poisson, from a long time ago, is simply the probability of these certain rare events. And he calculated it this way, where we have this rate of those rare events. You would have to obviously know what that is if you had a distribution table that you're calculating. And this is all, remember that we're dealing with a natural logarithm kind of mathematics here, where e is just simply the base of the natural log. So it's this random variable that we're waiting to see how many might occur, and it gives you this distribution that's again skewed relative to a normal distribution. Okay, so I've glided through these pretty quickly. We haven't sweated the math too much, but I think you need to remember that these could be very handy for you. Why? Why do you need to learn about these things? Well, let's go back to the normal distribution we spent a lot of time on. It's classically used in a lot of the traditional statistics. It's commonly assumed if you have really large samples. One way to try to work around that is to do transformations. I hinted at that momentarily. We're going to come back to those later in other course sections or in labs, where you can make, for example, a log transformation of data to get it to fit your normal assumption for a lot of statistics. But there are some nice methods now where you don't have to sweat that, and you can say, I'm working with a Poisson distribution, which is commonly assumed, by the way, if you have count data, and it works quite well. And if it's even more over-dispersed, which I'll explain in just a moment, you get even more variation, for example, broader tails, then you might be able to go to a binomial or a negative binomial distribution. Let me show you an example. Here is a data set from this paper where they're looking at negative binomial distributions for counting ecological data. This is, let's see, autumn migration of woodlarks in a field station, etc. Okay? So this is the days of the year, and they're counting how many birds did they see on those certain days of the year. So this is the progression through the year, right? And so if you try to fit a distribution to that with a Poisson, you can see that it's really not working very well. There's a lot of points that are high and low and not really represented very well by that Poisson distribution. They played with a couple different kinds of negative binomial distributions, and they had a combined one. And their point was that using a negative binomial, either one or the other or this combination version, they could fit pretty nicely the probabilities of observing a certain number of birds on certain days of the year at this place. Okay, so a negative binomial is often pretty good, as might be a Poisson, for count data. Okay, so you're going to find that normal distributions can work with plenty of data, but when you have at any given day, for example, in this data set, or even lots of other situations, a Poisson or negative binomial distribution can work quite well. Okay, so again, why do we need to learn about these things? Well, a normal distribution is assumed in ANOVA's regressions by default. You might be able to get your data to look normal if you do some transformations, for example with logarithms, but you can use a Poisson, a negative binomial, and because it might work better in more advanced methods. And there's even, by the way, a zero inflated method, which we won't go into because frankly the math is pretty complicated, but you need to know it's available, and again in R it's just available with a click or typing in a short command where you can say I'm going to use a zero inflated negative binomial, for instance, and what that's essentially doing is saying you have more zeros in your data than you might expect with a regular negative binomial, and we can address that in basically a two-step analysis. Account for the zeros, fix the distribution to look more like a negative binomial, and then evaluate the data with a binomial or negative binomial distribution. So you have some pretty advanced methods at your fingertips to go beyond the normal distribution. It's not something that's been always available to lots of people. If you look through historical literature, there's lots of efforts to try to get data to look normal. I've done this a lot, my students have done this a lot, and it can be very frustrating. We're liberated from that now by being able to say, not a problem, I'm working with an analysis that allows me to say Poisson or negative binomial or something, and it works far more comfortably, makes your analyses more robust and less vulnerable to criticisms. Okay, so we've talked about a few different kinds of distributions fairly briefly, and that's probably all right. We don't need to sweat those equations too much. Remember that the normal distribution is assuming this lots of points and giving you this shotgun pattern that you can express from left to right. But we have to be careful in evaluating that. That is an assumption of classic statistics, and you'd better check that normal distribution assumption. There's a classic way to do that visually with the normal probability plot. We'll work with those in course in the labs, but I'm going to emphasize you guys should also be using Shapiro Wilk tests as well. And then let's remember that there are these other distributions which we'll be working with later in the semester too, which free you up from this constraint of normality. Because after all, what is normal anyway? Okay, enough about that. We'll be working with these quite a bit coming up in the course in labs and in homeworks. All right, that's it for now. Bye.